Let's look at number 12C. So a student measures the absorbance of, it looks like 1, 2, 3, 4, 5 different concentration solutions. And they're making this graph now, as we'd expect, as you get more concentrated, the solutions just start to absorb more. Like say for instance, this one over here is the 0.02 molar one. It's the most dilute one. And this one over here is the 0.1 molar one. Well, the more dilute one, of course, as light enters the solution, because it's dilute, it won't absorb very much light, and most of it will pass through. So the absorbance should be very low, which it is. The 0.02 one absorbs hardly any light. And then when we look at the more concentrated solution, as the light enters the solution, more of it will get absorbed, and very little will come out the other side. And so we see that here, as the more concentrated one absorbs a whole bunch of light. Now, the reason they did this is called a calibration chart, and it will help us solve C. So in C, they want us to, they say the absorbance of the unknown solution is 0.275. What is its concentration? And so literally we can just go up to the chart and find 0.275. Well, there's 0.25 right there. 0.275 looks like it's right about there. So I'm going to say it looks to me like right about 0.05. So the answer to this one would be 0.050 molar. And they didn't really say to explain your answer, so I think that that should be good. And we're going to use the same number of sig figs that they are indicating down here. Let's look at part D. They say that Beer's law is an expression that includes 3 factors that determine the amount of light that passes through a solution. Identify 2 of these factors. Well, we know that Beer's law is absorbance equals molar absorptivity times path length times concentration. You know, another way to write it is A equals ABC. That's the one I think that's on the AP chart. You could do either one, it doesn't matter. But essentially all you have to do is say this equals molar absorptivity It says identify. It doesn't necessarily say to explain what they do, but the molar absorptivity is a constant that just tells you how much light gets absorbed. So the more colorful the compound, the higher the molar absorptivity will be. L is path length, and it might be a good idea to explain that. The path length is the width of the cuvette that you're using, because of course if you have a bigger width here, like if you have a cuvette that's much wider, it will absorb a lot more light. So that's why the path length is required. And that's 2. We know A is absorbance and C is concentration. So that should be good enough. Alright, part E, the student handles the sample container, the cuvette that holds the unknown solution and leaves fingerprints in the path of the light beam. How will this affect the calculated concentration of the unknown? Well, let's imagine this first one is a cuvette where light is passing through it. Some of the light gets absorbed. And in the second one, where the exact same scenario, but somebody gets fingerprints on the outside of it here. The fingerprints are going to block a little bit of the light as if it was the solution, and less light is going to come out the other side. So what are we going to conclude if that happens? Well, we're going to conclude that the solution was more concentrated than it should have been. So here's my answer. The calculated concentration will be higher than the true concentration. More light will be absorbed by the fingerprints than by the solution alone. Greater absorbance will calculate to an inaccurately large concentration. And I show the relationship using Beer's law. It's always a good idea to show a mathematical correlation. Increased absorbance will lead to increased concentration. And part F, why is this method of determining the concentration of cobalt chloride solution appropriate, whereas using the same method for measuring the concentration of sodium chloride would not be appropriate? Well, that's a pretty easy one. One of these two solutions is colorful, and you guessed it, that one is. Why is this one not colorful? Well, it doesn't contain a transition metal, and so therefore it won't have any color. So here's my answer. Cobalt chloride is a colorful solution and can absorb visible light. That's important for colorimetry. because we're using visible light here. Sodium chloride does not contain a transition metal and does not absorb visible light. So therefore we can conclude it will not work here.